So the idea with strong induction can be summarized in a radical difference with this logical formula. Okay, in this logical formula, we're stating that a certain property is true for a base case B, typically 1, and that for every k, if the property is true for k, then it's necessarily true for k plus 1. But once again, remember like the last idea that we discussed in the previous deck of slides, we checked a certain example in which if we don't carefully check other cases than the base case, okay, then assuming a false hypothesis may lead to a true implication, okay? So may lead to an implication that is true, yet the premise is not really true, okay? So this is one reason for using another strong assumption. And another example is this one, where you have a sequence that is defined based on the last 3 items in the sequence, okay? So an is equal to an minus 1 plus an minus 2, an minus 3. So in this case, if we want to prove this property, the fact that any item number n is less than or equal to 2 to the power n, okay? Then if we use mathematical induction only, given the property for 0, the first item, which is 1, it's less than or equal to 2 to the power 0. Okay, so the property is true; it holds for 0. If we consider an inductive hypothesis, the fact that the property is true for k, for an arbitrary k greater than or equal to 0, then we are assuming that ak is less than or equal to 2 to the power k. We need to show that the property for k plus 1 holds. The property for k plus 1 is the following, is ak plus 1, index k plus 1, is equal to 2 to the power, less than or equal to 2 to the power k plus 1, okay? And we know that a index k plus 1 is equal to a k plus a k minus 1 plus a k minus 2, okay, by definition, okay? So the element number k plus 1 is equal to the sum of the 3 previous items, ak, ak minus 1, ak minus 2. Okay, we can replace ak by 2 to the power k, actually. So on one side, we know that this is ak plus 1 is less than or equal to 2 to the power k plus ak minus 1 plus ak minus 2, okay? So according to our induction hypothesis, we know that ak plus 1, which is equal to this sum here, is less than or equal to 2 to the power k plus ak minus 1 plus ak minus 2. And that's it. How to proceed furthermore? Mm-hmm. If ak plus 1 is equal to this sum here, then since this item is less than or equal to 2k, okay, then this item plus ak minus 1 plus ak minus 2 is less than or equal to 2 to the power k plus ak minus 1. So I'm adding the same items to the right-hand side of the equation and to the left-hand side of the equation. Okay, so we could also start with this induction hypothesis, okay, which is ak equal to 2k. So we could start with this one and add to the left-hand side ak minus 1 and ak minus 2, and keep on the inequality by adding the same items to the right-hand side, okay? Plus ak minus 1 plus ak minus 2. So this is nothing else but ak plus 1. And now I have ak plus 1 less than or equal to this. Okay, good. Our target is to prove that is less than or equal to 2 to the power k plus 1, but we have no idea about how to deal with ak minus 1 and ak minus 2. Okay, so here comes the need for strong induction. Okay, so strong induction is quite similar to mathematical induction, except that we assume the property not only for k, okay, but we assume it actually for all. We assume that the property holds for all the integers up to k, okay, and we check whether in this case it's true for k plus 1, okay. And sometimes if we have such correlation between items in our sequence and more than one previous items, then we need to check 2 or 3 base cases first, and then we can use the induction hypothesis to prove the property from onwards. So how it works. This is the key logical reason behind how it works. So you assume that the property is true for 1, for 2, for 3, up to k, okay? And only in this case, you have to check whether you have to entail, or it's necessary to entail that the property is true for k plus 1, okay? If this is true, then for the same reason, it would be true also for k plus 2 and k plus 3 and so on and so forth. But on condition that you make sure that it's true for all these base cases, okay? Good. So this is called the second principle of mathematical induction or complete induction. Before giving a few examples, when do you use which one of them? So actually, you can always use strong induction instead of mathematical induction, okay? Because you are assuming more facts, okay? But there is no reason to use it if it is simpler to use mathematical induction, okay? So as simple as that. We can actually show that mathematical induction and strong induction are equivalent somehow, just by, it all depends on the choice of your base case and the how you state your property, okay? However, sometimes it's clear how to proceed using one of the two methods, but not the other, okay? So often it's up to you to pick up the right approach. I would tell that in such examples where you have properties about sequences and you have dependency on more than one previous value, okay, then you have to think about the use of strong induction. You will have a couple of other situations in the examples, okay? So let's consider the first one. We have to show that if n is an integer greater than 1, then n can be written as the product of prime numbers, okay? You know this Euclidean decomposition of numbers into prime numbers. We used to do it to check the common factors of two different integers, okay? So let P of n be the proposition that n can be written as a product of primes. The basis step is P of 2, and it's true because 2 can be written as itself, as the product of nothing but 2, okay? And 2 is prime, so the property is true for 2. Well, the inductive step in strong induction is completely different from the inductive step with mathematical induction. So here we assume the hypothesis that the property is true for J, for any J, such that J is greater than your base case and less than or equal to K, okay? So for any K, we assume that the property is true for all the J's that are between your base case and K. So here we have P of 2 true, P of 3 true, P of 4 true, and so on and so forth, up until P of K. And we want to show that P of K plus 1 is true, okay? If you make this assumption that 1 is prime number because 1 is only divisible by 1 and itself, okay? So in this case, yes, can do the same as we did with 2, okay? but I think they do not consider 1 as a prime number, if I'm not wrong. Yes. Sorry? In yeah, yeah. For this case, we want to prove it for an integer. Okay. Yeah. Yes. Um, sometimes in your exercise, in your context, you cannot assume this, or assuming this anyway won't help you in proving k plus 1. Okay, so this is why strong induction is you have a stronger assumption, you have a stronger claim about your hypothesis. Okay, inductive hypothesis. So maybe you don't need it. Okay, maybe you just have to look one step backward to the property at the step number k. But if the nature of your problem really depends on previous values less than k, then you have to make this assumption. If you fail anyway in proving the property for k plus 1, then it means that your property does not hold actually for every n. There is a problem with it. Okay. But if you succeed in proving it, then you have to have this confidence in it, and you can check whether you have any pitfall anyway in certain base cases. Okay. So we want to prove the property for k plus 1. So we have two different possibilities, two different cases. So either k plus 1 is prime, and then the property is already true because a prime number can only be written as itself multiplied by nothing else. And in this case, the property is true because we can write this number as a product of prime numbers, okay? Given that the smallest product is a single number multiplied by nothing, okay? Otherwise, if it is a composite number, then it can be written as the product of two positive integers, okay, a and b. And typically, these numbers, or necessarily these numbers, are between 2 and k plus 1. Okay, they are greater than or equal to 2 and less than or equal to k plus 1. Okay, so for example, if we're thinking about 6, let's say, so 6 is the result of the multiplication of 2 and 3. Okay, these numbers are between 2 and 6 included. Okay, strictly less than 6, sorry, but greater than or equal to 2. And it happens that they are prime numbers. Okay, otherwise, even if they are not themselves prime numbers, but at least according to the assumption that we made, that for all the numbers j's, the property holds, okay, then it means that a and b themselves have this property, okay? So since we can write a as a product of prime numbers and b as a product of prime numbers, and k plus 1 is nothing but the product of a and b, then finally k plus 1 is a product of prime numbers altogether, okay? Is it fine? Yeah. Somehow, yes. Yes, induction, when you have recursive functions, so often if you want to prove properties about them, you will use induction and recurrences, okay? Yeah, absolutely. So once again, what we are having here is k plus 1 equal to a times b. And according to the induction hypothesis, a is a product of prime numbers, prime number 1 up to prime number a. And well, let's use n. And then multiplied by b, which is, so this is a, and you have b here, so you have prime number 1 up to prime number m, okay? So finally, k plus 1 must necessarily be written as, oh, can be actually, it can be written as a product of prime numbers, okay? Good. Any question about this example? Okay. So let's use it to prove a weird property, which states that every amount of postage of 12 cents or more, 12, 13, 14, 15 cents, can be formed using just 4-cent and 5-cent stamps. This is a nice property for a state that wants to charge people for postages that are greater than or equal to 12 cents. Instead of creating all sorts of combinations, they would just create 4-cent stamps and 5-cent stamps. Okay? But how to prove it actually? If you start checking the first cases, okay, the property for 12, for example, so you can use 3 4-cent stamps to create this 12 cents value, okay? And you can use 2 4 and 1 5 cents, okay? So 2 4, it's 8 plus 5 equal to 13, okay? For 14, you can use 1 4 and 2 5s. For 15, you can use the 3 5-cent stamps, okay? So typically with strong induction, you would find that you need to check more than one basis step, okay? And then the basis steps will be will recursively actually reiterate afterwards, okay? So imagine that you assume this inductive hypothesis, the fact that P of J holds for any J, okay? It's a very strong claim, I totally agree. But you will see that we can argue just using these 4 facts that we can finally rewrite it for K plus 1. Actually, we can dictate the same property for K plus 1. And the reason is, so using the inductive hypothesis, the property for K minus 3, which is K minus 3 is less than or equal to K, okay? So it must be true, the property must be true according to our assumption. So the property holds for K minus 3, okay? Since K minus 3 is greater than or equal to 12. And why? Because we are considering all the Ks that are greater than or equal to the highest base case. Okay, so we checked for 12, for 13, for 14, for 15. Now we want to make this assumption that from 15 and on, for any K that is greater than or equal to 15, the property holds, okay? Including for these 4 cases, of course, okay? But our assumption only considered the case that are greater than or equal to 15. So the any K minus 3, okay, has this property, okay? For 12, 13, 14, and 15, we are sure, okay? And for all the others, if you consider 16, then you know that P of 13 is true. If you consider P of 17, you know that P of 14 is true, and so on and so forth. So using the inductive hypothesis, the property holds for K minus 3, since K minus 3 is greater than or equal to 12. To form postage of K plus 1 cents, all that you need to do is to add 4-cent stamp to the postage for K minus 3. Okay, and bingo, you will have a stamp with the right value. Okay, but don't forget that you have these basis steps. So you will always have these 2 5s or 3 5s or 1 5. Okay, or 0 5. So the trick is actually to get any number, it's either odd or even. Okay, and you are starting from 12. So 3 4s gives you an even number, which is 12. Okay, 3 4s, yes. But if you want to get the next odd number, then you have to replace one of the 4s with 1 5. Okay, as if you were adding 1 to it. Okay. If you want to get to the next even number, then you have to use 2 5s and 1 4. Okay, if you want to, and so on and so forth. And this would repeat indefinitely. So just add 4 to one of these, and you will obtain 16. Add 4 to this, and you will obtain 17. Add 4 to 14, and you will obtain 18. Add 4 to 15, and you will obtain 19, and so on and so forth. And this cycle will repeat again and again and again. Okay, so this is why we have these four base steps. Yes. Yeah, as long as you didn't repeat your reasoning in your base cases, then you can still proceed. Okay. So here, what you will notice that to get to 16 or 17 or 18, 19, you only have to add 4. So the repetitive pattern starts from 16 and on. So this is why we stopped here. Okay. The only differences are in the 4 first base steps. Yes. Yes, sure. Mm-hmm. Sorry, how? Didn't? Sure. Sure, sure. Yeah. It's what we have proved is that there is a way to represent any other number just by adding 4 to it. Okay, so as if we are going periodically and adding 4 to one of these 3 items or their next 4 items. Okay, um, but it's true that we could rewrite 16 in a different way. We could use 3 5s and 1. No, actually, we cannot do it. So actually, two 5s and I don't know. Okay, so maybe you can do it. Yeah, maybe you can do it in another way. Okay, I totally agree for large numbers. Okay, but it is sufficient to do it in one single way. Okay, and this is what we have proved here. Okay. So I totally understand your concern, but we just picked up a straightforward way to do it. Okay? Yeah. Yeah. Unless it's an exam and you are asked to do it by strong induction, then you are free to do it. Yeah, in no matter way you see it fit. But typically, if you would prove it for um, let's say a recursive function, then usually recursive functions they asks for induction. Okay, it's much easier usually with induction. Good. So yeah, I think they proved it here. Inducting stones. So a very weird problem, other weird problem. Take a pile of n stones or coins, whatever you want, and split the pile into 2 smaller piles of size R and S. Okay. Let's say you have 7 coins, then you split them in 2 piles of 3 and 4, or whatever you want, 4 and 3. You could do it also with 2, 5. You can do all the possible combinations, and you will still have this property true. It's a very awkward thing. Repeat until you have n piles of 1 stones. Okay, so maybe you cut it here in 3 and 1, or 2 and 2. It does not matter. Maybe you cut this one into 2 piles of 2 and 1, 2 piles of 2 and 1. Finally, this one is a pile of 1 and 1. And same here. Okay. So if we take the product of all the splits, so I need to change a little bit the color. Okay. So if we take the product of all the splits, so all the R's and S's from each split. So for example, here, let's say R and L instead of S to say right and left, okay? So the product here is equal to 12. 4 times 3, it's equal to 12. Here it's 2 times 1, it's equal to 2. 1 times 1, it's equal to 1. 3 times 1 is equal to 3. 2 times 1 is equal to 2. And 1 times 1 is equal to 1. If we sum up each of these products, so 12 plus 3 plus 2 plus 2 plus 1 plus 1, I think we obtain something like 15, 17, 19, 20, 21. Okay? So we can prove that this product is equal to n times n minus 1 over 2. Bingo. So it's, in our case, it's 7 times 6 over 2, which is really true. Okay, it's equal to 21. So assume that the sum of the products when n is equal to 1 is 0. Okay, because we cannot divide a pile that is equal to 1, or just in case you would divide it into a pile of 1 and a pile of 0 stones. If you do the product, it's equal to 1 times 0, it's equal to 0, okay? We could consider another base case for 2, for example. For 2, it's 1 and 1, if you multiply, okay, and then you obtain the right answer. So here you have another example in the slides, and you can check that it really works. So how to prove it? So you have to assume the property is true for k stones. The basis step is n equal to 1. 1 times 1 minus 1 over 2 is equal to 0, so it's okay. Anyway, we are assuming this fact, okay? And the inductive step, we assume that the property is true for 1 stone, 2 stones, and so on up to k stones. We need this because we don't know how we are going to split k plus 1 stones, okay? So we need, no matter how we split the k plus 1 stones, we need to have a certain idea about the pile to the right and the pile to the left, okay? So this is why we need a strong induction in this example, okay? So it means that P of j is true for every j greater than or equal to 1 and less than or equal to k. We need to show that P of k plus 1 is true. So to proceed, we are gonna split the k plus 1 pile of stones into k plus 1 minus I and I stones, okay, to the right and to the left, okay? So if you pick up I stones from the k plus 1 stones and you put them in one basket, in one pile, then you will end up with k plus 1 minus I stones on the other side, okay? In your final product, in your final sum of products, you will have I times k plus 1 minus I, okay? As we had in the 7 division into 4 and 3, we had 4 times the 3 in the sum of the products. But we also have to sum it up with the recursive divisions, product of the divisions of the pile with I stones, and the recursive subdivision of the k plus 1 minus I stones, okay? So, and this is a recursive function. We don't know how, what's the value of it, but we can assume a certain property about it because I is strictly less than k plus 1, okay? And k plus 1 minus I is also a number that is less than k. So both of them can be considered as j's for which the property holds, okay? So we want to prove that this is equal to k plus 1 times k over 2. So let's check if we can do it. So this is the product of the two piles at the current split. Si is the result of splitting the pile which, with I stones, and sk plus 1 minus I is the result of splitting the pile with the k plus 1 minus I. So since I is less than k plus 1, then it means it's less than or equal to k, okay? And k plus 1 minus I is also the same. So we have the property for I and the property for k plus 1 minus I, okay? Let's see how this helps us in proving the original property. It's one possibility. I might be equal to 1. I totally agree. So if this is what you mean, Andre, then I totally agree with you. Okay, this is a special case. When you, for example, in my example of 7 stones, I could split them into 6 and 1. Okay, and then the 1 is like, I have nothing to do with it. 1 times 6 is equal to 6. Okay, this is the I times k plus 1 minus I. It would be equal to k plus 1 minus I, yeah. 7 minus 1. Yeah. For all the j's actually, in the assumption, we're assuming that p of 1 to j, k, etc. is true. It means it's true for all the j's that are between 1 and k. We could do it this way as we did with the four stamps, and we took only one possible solution of splitting and show that we can split them in a way so that the product is equal to that thing, but without loss of generality. We can prove it with for every I, such that I is less than or equal to k stones. Okay, so it could be if you only take one stone and you keep k stone on the other side, or you take two and you keep k minus one, and so on and so on. So for any value, this would work. Okay, so it's just a stronger way to prove it. So having the property for I and for I need to switch to red. So having the property true for I and for k plus 1 minus I means that you're assuming that the sum of the product of the ways you are going to split your I stones is equal to I times I minus 1 over 2. Means I squared minus I over 2. And assuming the property for k plus 1 minus I is assuming this. And this is the development of this term. So what you want to prove is this multiplication, I times this term, plus s of I plus s of k plus 1 minus I, you want to check whether it's equal to this term here. Okay, it's a bit tedious, but it's straightforward. You do the math, and you get rid of all the I items. You will end up with k squared plus k over 2, which is k times k plus 1 over 2. Okay, according to our target formula, they must be split. Okay, it's n times n minus 1 over 2. Okay. Okay, good. So the only idea here is that you need to make an assumption about two previous items. You don't know which one. Okay, it's quite similar to the decomposition of integers example. Okay, so we know that if the number is prime, so we can write it as a product of prime numbers. Otherwise, we can write it as the product of two integers a and b. And since we are assuming the property for all the integers that are less than the current one, then it holds for a, it holds for b, and then finally the integer would be the product of all the other prime numbers. One last example is for what values of n can a square be subdivided into n subsquares? Mm-hmm. No, not really. Let's make the first steps. How can you divide this one into perfect squares, smaller than this one? So if we just put one line in the middle, we will obtain two rectangles. Okay, to keep on squares, then we need also to put another cross. Okay, so the typical example is this decomposition into four different squares. Can we split a square, the original one? Can we split it into two squares? So we can use diagonals to split it into two different geometrical shapes, but they won't be. Let's check other cases. Nice tries, but actually let's check. I think we can split it in almost all the integers except a few cases. And I was discussing with you these special cases. So we cannot split it into two. Do you agree? A square, we cannot split it into two perfect squares. Okay? No matter where you put your line, if you use only one line, you will get two different geometrical shapes. They will be trapezoids, triangles, rectangles. Okay, but you cannot get two perfect squares from one with one line. So if you use two lines, then you will obtain at least 4 different squares. So I think even if you try to think about having 3 different squares inside the original one, it won't be that easy. Okay, so you will often, so once you use a crosshair like a two perpendicular lines, okay, you can move them a little bit. Okay, so I can move the center to this vertex here, but I will obtain a square on this side, a big square to the left upper side, but I will start having rectangles on both sides here and there. Okay, so it won't work. Maybe the rectangles that I will obtain, I can cut them into squares, but then I will obtain more than 4 items. Okay, more than 4 rectangles. And by the way, I cannot even obtain only 5 rectangles, 5 squares. Okay, so imagine that I'm dragging this center to this diagonal point here. Okay, this will create one perfect square here. So if you start dragging this to this side, so eventually you will obtain this shape here. So this is a perfect square. Do you agree? And this is a perfect square. Good. But these are rectangles. Okay. So maybe you can get exactly to the middle and cut them into squares. But then you will obtain 6 different squares. Do you agree? So 1, 2, 3, 4, 5, 6. Okay. So once you start dragging your perpendicular lines, okay, you start creating rectangles that must be cut into 2 halves to have perfect square. Okay, and the number would be automatic. You have to cut both of them because they are of equal size. So you jump automatically from 4 squares to 6 squares. There is a certain pattern. So we cannot reach 2, we cannot reach 3, we cannot reach 5 squares. But actually, we can reach 6. Can we reach 7? 7 squares. Hmm. What if I reconsider this same original shape? And I think now you will, starting from 6, you will see a certain, you will notice that there is a certain pattern. So can I subdivide one of these squares into 4 squares? Okay, so if I had originally 4 squares, I'm taking out of them one of these squares and I'm replacing it by 4 other squares. So as if I'm adding 3 to it. No, okay. So because if I do the same splitting, okay, once again, so I have like one of them counts for the original big square that was on this corner, okay, and I'm just adding 3 additional squares. So please do the count with me. I had 4 different squares. Now I have 1, 2, 3, 4, 5, 6, 7. Okay, so I showed you that we can obtain 6, we can obtain 4, we can obtain 1, and now we can obtain 7. So let's check if we can obtain 8. Okay, so once you start adding 3 at each time, so you can get to 7, to 8, to 9, and so on and so on. Yes. We added 4, yeah. But so we had 1, we subtracted 1, and we added 4. So this is why we ended up with 4, and we cannot add, we cannot reach 2 and 3. Okay. For 5, it's impossible because because of this dragging of the center. Okay, so once you create a rectangle to this side, you will create a rectangle on the other side, and then you are adding 2 squares at once. Okay, so you are subtracting 1, you are subtracting 1, and then adding 2, so as if you were adding 2. So you jump from 4 to 6. Okay, you cannot create 5 squares. Okay, but you can obtain 7, and you can think of cases where you can obtain 8, 9, 10. Actually, you can do whatever other decomposition afterwards from 6 on to obtain all the other cases. So here it's a decomposition into 9 squares. You can subdivide, as I told you, into 6. You can subdivide into, I think, 16, and 5 it's 21. So actually you can get any integer, but only from 6 on. Okay, so you cannot reach 2, you cannot reach 3, you cannot reach 5, but all the other integers can be used as the number of squares. So the key insight once again is what I just told you. So we are subtracting 1 and adding 4, so as if you were adding 3 all the time. And this is why you need to prove your case for 3 base cases. So since we can subdivide a bigger square into 6, 7, or 8 squares, then we can subdivide the square into n squares for any n greater than or equal to 6. Okay? And for the special case of 1 and 4. So this is the conjuncture. This is what we want to prove. Okay? That we can divide a square into any number of squares that is greater than or equal to 6. But the base cases would be 6, 7, and 8. Why? Because each time, if you have 6 squares already, you can take one of them and subdivide it in the way that we just mentioned. Okay, which means you're taking that square and adding 4 instead of it. So you are adding 3 squares to the total number of squares. So you can obtain 9. From 7, you can obtain 10 squares. From 8, you can obtain. You have a very nice animation here. So if you have these 3 base cases, 6, 7, or 8, if you consider the 6 squares division, given your assumption, you can get out 9 squares, okay? And then you can reuse it now as a new rung on your ladder to climb to 12 squares, okay? 6, 7, and 8, okay? So now from 7 you can reach 10 squares, from 8 you can reach 11 squares, okay? And now you have 3 new base cases, 9, 10, and 11. And then from them you can reach 12, 13, and 14 squares. And from there you can reach 15, and so on and so forth, okay? So this is it for strong induction. I will upload the video as soon as possible for your colleagues, and I'm ready to answer all your questions, including your emails. I didn't read everything, but